Welcome to this presentation. What I want to do in this segment is to motivate the convolution integral using a discrete time example. I want you to try to get a basic understanding of why this convolution integral has the structure that it does. Why does it involve the impulse response and the input in the manner that it is combining those, and in particular in this particular convolution integral that you see on the screen is h of t is the impulse response of an LTI system or a linear time invariant system. X is the input to that system, or the input that's applied to a system that has the impulse response h of t, and if we want the output of that system due to the input x of t, we can compute this integral to find the output y of t for all time t. If we do that, what we really are seeing is that we simply need to put in the variable of integration for our impulse response, or change h of t to h of tau. But for the input, what we need to do is actually take the original input, x of t, replace time with its reflection, make that x of minus tau, because tau is our variable of integration. Then we essentially start to slide that input, x of t, through the impulse response and integrate that product of the input with the impulse response as we're sliding the input through the impulse response as a function of time. And as we compute that integral, we will obtain the output response y of t. What I want to do is try to provide a connection of that particular convolution integral with this discrete time convolution sum. I'm going to work an example that involves discrete system response and discrete inputs, and hopefully that will be somewhat intuitive as to what's going on. What we will find is that we actually end up with this convolution sum in the discrete time setting. And if you now compare the two time domain versions, you have the continuous time up above and the discrete time down below, you can see that the integral becomes a sum, the impulse response is still in the same location, it's now called what I call a pulse response, and the input is also x. It's now just a discrete time input, and our output y is what all of that convolution sum provides, and that's just y of n on the left hand side. We'll then use or see that this example will produce this convolution sum, and hopefully then in the limit as the sampling becomes very, very close, you can see that this convolution sum actually converges towards this continuous time convolution sum, and hopefully that will provide you with a better intuitive feel for this convolution integral, which we will be applying throughout the semester. Again, h of n is the pulse response of a linear discrete time system. It's also time invariant. X of n is the input, and if we compute this convolution sum for different values of n, or for all values of n, from minus infinity to plus infinity, we will obtain the output response y of n for all time. Let's do this, or try to motivate this convolution sum equation via an example. And this example then will begin with two pieces of information. We need the system, and we will actually define the system by means of its pulse response, or we are now looking for h of n. And we also need an input that is going to be applied to the system, and that input we will call x of n. Let's now just select a pulse response and an input for this example system. Suppose that our time index is n and our pulse response h of n. If we applied a pulse, a value of 1 at time n equals 0 to our system, the pulse response is how that system will behave or dance or move in response to that unit pulse that's applied at time n equals 0. And how long it shakes or moves is obviously associated with that particular system's behavior. Here, let's just give it a finite duration for its pulse response. Let's say that if we apply a pulse of magnitude 1 at time 0 to our system, the system will now behave in such a manner that immediately its output will become 1/2 at time n equals 0. We now do not apply any more inputs to the system, but it now continues to evolve. And let's just, this is hypothetical, let's say now that it increases up to 1/2 or 3/2 at time n equal 1. At time n equal 2, it grows to 2. Now at time n equal 3, let's say that it starts to die down in terms of its response behavior, and by the time n equal 4, let's say that the response is completely gone in the system from a pulse that was applied at time n equals 0, and we now have this finite duration pulse response due to a pulse applied to our system at time n equals 0. That's how our system behaves relative to a pulse input. But typically we don't have just pulse inputs to a system, just like we don't apply all the time an impulse response to a system and say, well, this is all the system is ever going to see is this impulse response. No, it's going to be some other system signal input, and what we do though is we try to determine what the specific output response is going to be for each specific input, but that really only requires us to know the impulse response of the system. That's what the convolution integral will allow us to do. Now for our input, let's say that we now have an input to the system, x of n, which is not just going to be a pulse. Let's say that instead at time 0, let's apply a value of 2. At time n equal 1, let's continue to apply an input to the system, except now let's change that to a value of -1, meaning we now have some shape to our input. And let's say that at time n equal 2, we now apply a value of 1 to our system. And by n equal 3, let's say that we're finished applying any excitation to the system. Our input is now 0 for time after that. What I maybe should have done was sketched h of n and x of n, but let me do it now so that you get a feel for what we have. The pulse response of our system was h of n, and this is a time domain plot. We said if I can scroll just a little bit, now we know what our system response is going to do when we apply a pulse. It's going to, at time 0, it's going to have a value of 1/2. At time 1, it now grows to a value of 3/2. And if you want to sort of make the distinction that these are discrete numbers, or I'm sorry, they are values at discrete instances of time, n equal 1. At time n equal 2, our input is 2. At time n equal 3, our input is now decayed down to 1. And at time 4 and all time thereafter, we have 0 response from our system. That's what the pulse response looks like. Now let me try to quick slide in the input that we are going to apply to our system. Here is x of n. Here's 1 and 2. My scales have changed, but hopefully you get the idea. And here's minus 1. Here's 1, 2, 3. There's n equal 1, n equal 2, and n equal 3. And for our input x of n, let's now say that at time 0, we said that we were going to apply a value of 2. At time 1, we apply a value of minus 1. And at time 2, we apply a value of 1. Let's now see what we obtain for the total response when we apply this sequence, input sequence, x of n, to our system, where our system is described by this pulse response h of n. Meaning we should just see a linear combination of these pulse responses, which is really what we do when we apply any signal to an input, a linear system. We're just going to get a combination of how that system responds to an impulse in the continuous time setting. For this, we are dealing with a linear system, and because we now have a linear system, we get this powerful this powerful property, which is superposition, and that superposition holds. What we are going to do then is we are going to apply the input at time n equals 0 and look at its response. Then we will see what the system does when we apply this input at time n equal 1. And finally, we will see what the system does when we apply this input at time n equal 2. To get the complete response of our system, we simply have to add all three of those components together at the appropriate times to obtain the complete output response of our system. That's what I want to write now. We want to calculate the total response or output response, y of n, due to the application of the input x of n to the system, where the system has this impulse response, or I should say pulse response. In a discrete time setting, I try to distinguish between continuous time and discrete time by using impulse and pulse respectively, to the system with pulse response h of n. Or the other way of thinking of this is that the output of our system will actually be a combination of the system response caused by the input applied at all time, and in this particular example we really only have 3 times that we're applying an input value. So the output will be a combination of the system response caused by the input applied at n equals 0. It will have a component due to the input at n equal 1. And finally, it will have a component of the output due to the input applied at n equal 2. If we can now compute all 3 of these responses due to the input at 0, 1, and 2, then we can add those responses up, because it's a linear system and superposition applies, to obtain the complete or total output response. So we will use superposition to determine y of n. Let's now do this. Let's do each of the pieces separately, and then we will, at the end, combine them up to get the total answer. Let's now look in this first piece at our output response due to the input applied at time n equals 0. So we now want the output response due to x at n equals 0, which I will denote x of 0, and recall what that value was. Numerically, it had an input value of 2 at n equals 0, where this is now the input at time n equals 0. To help keep track of everything, let's now label this particular component with a unique variable. Let's call this output component due to the input at time n equals 0. Let's give that a subscript 0, meaning this particular n equals 0 is giving rise to that subscript 0 in the labeling of the output due to that particular input. And this particular component right there, which is this guy, this is now the component of the output due to the input that is applied to the system at time n equals 0. Let's now see what that is. If we go back and we look at the pulse response, the pulse response is h of n. We would get 1/2, 1.5, 2, and 1 if we applied an input of magnitude 1, or a unit pulse. What we're doing now is we're applying a pulse at time 0 with amplitude 2, which really says, oh, we have the pulse response with an amplitude of 1 applied at time 0. All we really need to do, because of this linear system, is scale each of those values of h of n by a factor of 2 at the appropriate time index to obtain the component of the output due to the input applied at time n equals 0. I hope that was clear. Let's now sketch that or draw that particular response. We now are saying that we have, due to the input applied at time n equals 0, we are going to create